de la sección de Física y Química y dejaré la verdadera presentación al académico Luis Liz Marzán. Y me excuso por el retraso que hemos tenido y por el orden en que hemos hecho. Haremos la entrega del diploma y la firma en el libro de honor después. Es decir, que eso quiere decir que a ver si podemos acabar la charla y la presentación para las 7:30. Bien, y sin más, dejo la palabra.
Muchas gracias. Buenas tardes a todos. Para mí es un placer inmenso presentar la sesión científica en la que el profesor Mauricio Prato nos va a hablar de química, nanotecnología y la resolución de problemas imposibles. Antes de darle la palabra al profesor Prato, querría dar unas pinceladas de su perfil y de aquel que va a ser el ponente y también un nuevo compañero en la academia. Mauricio Prato es catedrático de Química Orgánica en la Universidad de Trieste y además es profesor Ikerbasc en el Centro de Investigación Cooperativa en Biomateriales, TIC Biomagune, en San Sebastián, desde hace ya 7 años, donde lidera el Laboratorio de Bio-Nanotecnología del Carbono. Ha publicado más de 700 artículos a lo largo de su carrera en las revistas más prestigiosas de química y ciencia de materiales y que han tenido un impacto tremendo reflejado en más de 60.000 citaciones y con un índice H superior a 120. Entre muchos otros galardones que ha recibido, se puede destacar que es miembro de la Academia del Lincei en Italia, es miembro de la National Academy of Inventors de Estados Unidos y también de la European Academy of Sciences. Hoy tenemos el honor de entregarle el diploma acreditativo como miembro de la Real Sociedad Española, perdón, la Real Academia de Ciencias Exactas, Físicas y Naturales de España. El profesor Prato es conocido internacionalmente como pionero de las estrategias más eficientes para la funcionalización de nanoestructuras de carbono, dentro el contexto de una de sus invenciones originales que se conoce ya como la reacción de Prato y se utiliza en muchas universidades y centros de investigación del mundo para buscar y dar mayor utilidad a estructuras como fullerenos, nanotubos de carbono o grafeno. Además, estas estructuras tienen aplicaciones en campos muy diversos, desde la medicina hasta la producción de energía. Como ejemplo que se puede destacar, pero él nos va a contar más dentro de un momento, es el proyecto que está desarrollando dentro de una cátedra de la Fundación AXA, donde desarrollan andamios fabricados con nanotubos de carbono para regenerar la conexión entre células neuronales en médula espinal, como posible solución para problemas de accidentes de médula. Por lo tanto, un impacto social también potencial tremendamente importante. No me voy a extender más, simplemente ceder la palabra a este extraordinario científico y entrañable amigo, profesor Mauricio Prato.
Muchas gracias, Luis. ¿Podemos ver la presentación? Sí. Señor presidente de la Real Academia de Ciencias, excelentísimas señoras académicas y señores académicos, amigos, señoras y señores, agradezco el gran honor de haber sido admitido como miembro extranjero en esta prestigiosa institución. Este, como otros reconocimientos que he recibido en el pasado, debe ser compartido con todos los estudiantes e investigadores postdoctorales que han sucedido en mi laboratorio y que han sido el mayor estímulo para seguir trabajando cada vez mejor. Sin su talento y su continua y total dedicación, todo lo que he conseguido no habría sido posible. Quiero, por tanto, expresar Aquí mi especial reconocimiento a la contribución de varias generaciones de colaboradores por su excelente labor experimental y por las constantes discusiones de las que han surgido multitud de ideas y que me han permitido seguir aprendiendo a lo largo de toda mi carrera. Extiendo este agradecimiento a numerosos colaboradores en distintas partes del mundo, con quienes he compartido entusiasmo y emociones y colaborado activamente. Debo reconocer que España ha sido muy generosa conmigo. Recibí el premio González Chamichan de la Real Sociedad Española de Química en 2008. En 2016, gracias a Esther Vázquez, recibí el doctorado honoris causa de la Universidad de Castilla-La Mancha junto a Nazario Martín. Por lo tanto, mis vínculos con España son muy fuertes y están muy arraigados. Como miembro extranjero voy a hablar en inglés ahora. Why we decided to work on nanotechnologies or nanosciences, because in the field of nanosciences, which is the world of the small, organic chemistry, I am an organic chemist by training, organic chemistry can make really a difference because we can change the properties of the materials. We can add properties to this material, to the nanomaterials, and so we can completely make different materials starting from the original nanomaterials. And so in 1992, I went to work in Santa Barbara with Fred Voodoo, where many friends were also working with him, Nazario, Ángela Sastre, Fernando Langa, and Concepción Rovira, that later became very good friends. So when I went back to Italy, I had to find a way of functionalizing fullerenes in an original way, and I decided to use this reaction because this reaction gives full opportunity of placing the groups R1 and R2 on fullerenes. So as I was mentioning before, we can use essentially any type of R1 and R2 and decorate C60, add properties, and improve the solubility. This reaction was then extended to carbon nanotubes, which are much more difficult materials to work with. And this gave us, after a while, people started, this started in the United States because the American people are used to give names to reactions. So they started calling this reaction the Prato reaction. And this became very, very popular because this reaction was used in many, many laboratories. And I want to show here the contributions that Nazario Martin made to make this reaction even more popular. And frankly speaking, I have to be grateful to all these friends that used my reaction, giving the credit, the right credit. I knew Nazario in 1996 in a conference in Israel. You can see he was much younger, together with Harry Kroto, who unfortunately passed away very early. And then we became friends, and we met in several other places. Actually, in the early times, almost every year we could meet. Then another friend is Tomás Torres, and Tomás also used the Prato reaction very often. You can see here in the abstract he uses this reaction. You can see the 5-member ring here. And he also was very, very helpful in giving publicity to this reaction. Then other people like Fernando Lang, Angel Sastre, they were also popularizing the Prato reaction. Basically, what all these groups were trying to make, C6 is an excellent electron acceptor. And so in practice, if you shine light on a so-called diode, you have an electron transfer from the donor to the acceptor. And then there is a generation of the charge-separated species. And if the lifetimes of the charge-separated species is long enough, then we can recover the positive charge here and the negative charge here at the electrodes. And this is what several people did. You see, there were many people using porphyrins attached to the C60 still through the pyrrolidine linker. And what they wanted to do was to achieve electron transfer in order to have long lifetimes. So in principle, this should give rise to free electrons that can be collected at the electrode. However, it would be even more interesting to produce directly hydrogen from these reactions because, for instance, I mean, we are living very difficult times and energy is becoming more and more an issue because of the war in Ukraine and the increase of gas price. So the use of cars with hydrogen would somehow relieve this situation. However, today hydrogen is formed by steam reforming of methane at temperatures which are incredibly high and producing carbon dioxide anyway. So we would not get rid of carbon dioxide, we would still burn fossil fuels. And so I assume that if we look at the balance of pros and cons, we don't find really an advantage of using this. But this is actually the way hydrogen is produced today. However, nature uses the charge-separated species, so the light, to transform light energy into chemical energy. And in practice, water is oxidized to oxygen, and carbon dioxide is reduced to carbohydrates. And so the first challenge I want to talk today to you is the production of hydrogen starting from water. So in principle, water can be divided into hydrogen and oxygen, but this reaction is very, very expensive in terms of energy. So this would cost a lot of energy. Then hydrogen and oxygen can be combined in a very exothermic reaction in order to give water as a final product. So you understand that a car going with hydrogen would have only water as a product, and so this would be the ideal vector. So today, one possibility would be to use, well, this is not working. It doesn't matter. This is a simple electrolysis. So by placing a battery in contact with water, we can have generation of hydrogen on one side and oxygen on the other side. However, this process is also very expensive in terms of energy. And as you can see from this graph, the splitting of water thermal is very, very expensive in terms of temperatures and energy. But also the electrochemical splitting is a very high energy process because the energy required, I mean, this is the thermodynamic value, but then we have to include kinetic hurdles, which are usually grouped under the name of overpotential. So the electrolysis of water is very expensive, and so we need a catalyst to lower the overpotential. And so in practice, what we did in the past was the treatment of a catalyst like palladium and titanium dioxide in contact with carbon nanostructures in collaboration with Professor Paolo Fornasiero at the University of Trieste, and then the oxidation part in collaboration with Marcella Bonchi in Padova by placing her catalyst on our carbon nanostructures. And so basically with Paolo, we covered the nanotubes with a catalyst embedded in the metal oxide structure. And the method is very versatile because platinum and palladium can be used, and also the oxides can be titanium oxide, zirconium oxide, or cerium oxide, which possess different properties. So this material can be used for different applications. And so in practice, this is the way we synthesize them. And you can see from the electron microscopy that the original nanotubes are then covered with the metal oxide, and you can see the different structures. Actually, the nanotubes become thicker after the treatment with the metal oxide. So you can see also by electron microscopy the nanotubes covered with, in this case, cerium oxide. What we can say without wasting too much time is that in the end, in the presence of carbon nanotubes, we have an improvement of 200 millivolts in terms of reduction of energy required. And also, you can see this is the turnover frequency, so the speed of the reaction without carbon nanotubes and with carbon nanotubes, we have an improvement of about more than 2 order of magnitudes. So the other part, the oxidation part, starts with this type of material, in which we have to functionalize the carbon nanotubes in order to have sufficient attraction for the catalyst. So this is a very difficult process. Of the two processes, the reduction of protons to hydrogen and the oxidation of water to oxygen, the semi-reaction of oxidation is by far more difficult. And so once we achieve this reaction, the other one, it becomes very simple. In doing this, we started collaborating with Marcella Bonchi, and she had prepared this catalyst, which is a very impressive catalyst because it contains 4 ruthenium atoms, similar to the natural catalyst used by nature. So in practice, the catalyst needs to be oxidized, and then oxidation of water proceeds. So as a matter of fact, in Padova, Marcella and her co-workers were able to show that oxidation of water is a very favored process with a very good turnover number and very high turnover frequency. But if we place the catalyst alone on the surface, then the catalyst can go away because it is water soluble, and then it is too strongly packed. So it needs to be dispersed on the surface, and especially needs to be attached to the surface. So we decided together with Marcella to attach carbon nanotubes, the catalyst on carbon nanotubes. To do this, since the catalyst has 10 negative charges, we need to produce a nanotube with positive charges. And so we decided to use this dendrimer, which possesses several positive charges. And what happened was these arms of the dendrimer can electrostatically attract the catalyst. So you can see here the transmission electron microscopy images you see the shape of the nanotubes, but especially you see the dark spots are the catalyst, which is deposited on carbon nanotubes. And here you can even distinguish the individual catalyst adsorbed on carbon nanotubes. Here we can also see the distribution of heteroatoms. So we can see tungsten and ruthenium well distributed on the surface of carbon nanotubes. So in this case also, the device worked very well, and we had a really an exceptional boosting effect on high oxygen evolution using carbon nanotubes with turnover frequencies of a value which is very similar to what is obtained in solution. So we were able to reproduce on the surface the conditions that were produced in solution. So far we have talked about the electrochemical splitting of water, but nature does this with light. So we want to reproduce the photosynthetic effort, and in doing this, we have to take advantage of the knowledge. So when the crystal structure of the reaction center of the photosynthetic processes was discovered, it was possible to see that the disposition, we have a series of antennas which are around the reaction center. And so in practice, by using AFM, it was possible to see that, you see, these are the antennas that surround the reaction center. So in practice, the light goes here, it is collected among all these antennas, and then it is conveyed on the reaction center. And then the processes start. So the oxidation of water starts, and then all the other reactions. So if we want to reproduce this was called the quantasome, which is the smallest unit used by the photosynthetic pigments. And so if we want to reproduce this, we need to have a very strong structure in which we have a surrounding antenna together with a reaction center, the catalyst inside. And so we need a new catalytic system in which we have a catalyst and the antenna. And they should hopefully arrange in this way. And so we decided with Marcella again to use this type of materials which are called perylene bisimides, and they have a very extended aromatic system here. And because of the presence of these very strong electron withdrawing groups, it is a very electron withdrawing structure. And so since we have to somehow link this to the catalyst, we need positive charges. So we prepare this photosensitizer in order to assemble it together with the negatively charged catalyst. And then we need a sacrificial agent. You will see here, because once we irradiate the photosensitizer oxidizes because it's a strong oxidant because of the presence of these groups. It oxidizes the catalyst, and the catalyst oxidizes water to oxygen. At this point, to restart the process, we need to regenerate the neutral state here. And so we need to have a sacrificial oxidant, which is in this case persulfate, which can be dissolved in solution. And so we have this series of reactions occurring. So basically, this is what we want to achieve, in which we have the antenna surrounding the catalyst. And we have called this the artificial quantasome, which, if you see it from here, from the top, it should resemble this. What do we know about this? This is very specialized, so I will not go too much into detail. These are measurements with small angle X-ray scattering data together in collaboration with the group of Heinz Amenisch in Trieste. And what we discovered is that there is a precise distance between the heavy atoms. The vertical distance is about 2.3 nanometers, and the distance in horizontal phase is 1.6 nanometers. So they aggregate to form this type of structures, which can be detected by these X-ray scattering measurements. And so basically what happens is that the catalyst attracts the photosensitizer because of the positive charges of the respective charges, and then this forms a block which we can simplify in this way, and then this is a more extended structure, and this becomes a relatively large structure with the size that we have detected by X-ray scattering. And this is reminiscent of the natural chloroplast membrane, so we are able to reproduce the natural process, and also in solution we can see the evolution of oxygen in the presence of light. As you can see, in the dark nothing happens. In the presence of light we have production of oxygen, and this is our data, which is much better than all the other state-of-the-art electrodes that have been produced so far, even better than the natural system, the photosynthesis system too. So now this is what we have called, what is in general called artificial photosynthesis, and we are in the way towards complete artificial photosynthesis. So we take water and we oxidize on one side to oxygen, and on the other side we reduce it to hydrogen. So the second challenge, as Luis was mentioning, deals with the interaction of nerves and carbon nanotubes. So in practice, at a certain point, we noticed that the structure of nerves is very similar to the structure of nanotubes. And so we were thinking, why can we integrate carbon nanotubes with nerves in order to substitute nerves when they are not working anymore? And so in practice, this is a work of 20 years in which we started thinking about repairing spinal cord. The spinal cord is this cylinder that goes from the brain to it is contained in the bones, and contains all the nerves that then can go to all the organs, and they are controlled by the brain. So in practice, the brain sends the messages, and we have perfect control of all the limbs and hands, just because the nerves go from here to here, and then from here they go to all the organs. So whenever there is an accident and displacement of the spinal cord, here there is an interruption of the signal from the brain to the peripheral organs. And so in practice, whenever a lesion occurs, then there is no control anymore, and so there is paralysis. And paralysis can be either very heavy, depending on where the lesion is. Here, in practice, gives complete paralysis. If it's here, maybe only the legs. However, what happens in practice is that when a lesion occurs, and there is a lesion here, scars start to form, and the scars are completely insulating, but especially they block the growth of nerves from the two parts. And so what we thought a long time ago was, can we place carbon nanotubes here? Carbon nanotubes, they are conducting, they are metallic, so maybe if they integrate very well with nerves, maybe we can regenerate the signal between the upper part and the lower part of the lesion. And so this is because carbon nanotubes possess extraordinary properties, especially in terms of electronic properties, because they can be metallic or semiconducting. So in practice, what we did, we put in contact cell nerves, which are called neurons, with carbon nanotubes. And what we saw was that nerves, the neurons, start communicating much more efficiently among themselves. So carbon nanotubes actually serve to help neurons communicate much faster among themselves. And so after the initial studies on simple cells, we wanted to see whether organs can actually do this. And so we placed an entire slice of spinal cord on carbon nanotubes. And through in collaboration with Professor Laura Ballerini in Trieste, we can use this technique, which is called patch clamp, in which we can record the spontaneous activity. I mean, this, what the neurons do, they send messages in continuation to other neurons. And so in practice, we could record the spontaneous activities of the neurons contained in the spinal cord and see whether, with the presence of carbon nanotubes, they can communicate with each other, or we can even stimulate one slice and see what happens on the same slice and see what happens on the other slice. And so in practice, in this experiment, you can see this is the control, which is chicken plasmid, which is a nutrient for spinal cord explants. You can see that the spinal cord explants, they elongate their nerves with very strong fibers, but they don't seem to go in the direction of each other. In the case of carbon nanotubes, you see between the two spinal cord explants, we have a dense presence of nerves, which are very promising in terms of communication between the two slides. And here you can see the functionality. In practice, these are the signals. These are, each peak here is a signal that the neuron is sending around. So we have, this is a spontaneous activity of the spinal cord slide. And you can see the two slides are completely independent. They don't communicate with each other. And if we stimulate one, you see these dots are the stimulation. One slice, which is the same slice where we apply the signal, immediately reacts. You see, it reacts and then relaxes and then reacts again. So this reacts to the stimuli, so which is the same slice. The other one doesn't feel anything. So there is no connection between the two slices in the control. When we use carbon nanotubes, then we can see that already at the stage of spontaneous activity, the two slices are completely synchronized. So whatever happens in one slice happens on the other slice. And if we stimulate one, we have reaction immediately on one, but also reaction immediately on the other slice. So this means the two slices now are completely connected. Now, when we went in vivo, in the animal, in practice, this is work in collaboration again with Laura Ballerini in Trieste and with Pedro Ramos in Biomagune. In practice, a small piece of spinal cord was cut and substituted with carbon nanotubes. And what we can observe by MRI is that after 4 months, you see the lesion is still there in the reference. So we didn't place anything here. And so in the lesion, there is nothing. So nothing grew here. In the case of carbon nanotubes, you can see the lesion is completely filled with nerves. So nerves have regrown in the slice, in the lesion. And we could also see vases in the nerves, which means that not only nerves grow, but also vases with blood can go in. Then there is also the behavioral assessment. In practice, this is, I mean, there are tests that are used to see whether the rats can recover faster or slower. In practice, this is the recovery in the case of carbon nanotubes, and you can see which is much faster than without carbon nanotubes. This is called ladder. So they run on a ladder and they are observed. Also in this case, the recovery is much faster, much better in the case of carbon nanotubes. And also in this case, the footprint in practice, they observe the strength with which the paw is placed on the ground. And you can see that with carbon nanotubes, after 1 day, already most of the rats had started placing the paw with strength, with reference to the other control. And so in practice, the meeting of nanosciences with chemistry can produce very promising results, and we actually hope to solve these problems, which are really insurmountable. I mean, there are no cures available for the spinal cord lesion, and so this is a sort of promising approach. So basically, chemistry doesn't always get the right credit because always chemistry is associated with pollution and with damages. But chemistry has an enormous power. We can create things, we can make things and objects which never existed before, and especially we can look for possible solutions to impossible challenges. This is the group of people that in about 30 years, I mean, this is not updated, but they could not stay in the page anymore. And you can see here is the statistics among, I mean, except Italians, which of course it should be the majority, the Spaniards emerge. And in the years, we were very happy with Spanish postdocs and students. And finalmente, quiero terminar recordando que actualmente soy profesor Iker Vázquez en SIC Biomagune, en San Sebastián, donde desarrollo parte de mis investigaciones. Trabajando en Biomagune he recuperado la ilusión que tenía antes. Puedo trabajar en unas instalaciones de primer nivel y sobre todo he podido profundizar en mi amistad con Luis Marzán, al que ahora considero como mi hermano. Nos conocimos en México durante una visita para evaluar la investigación local en nanotecnología. Nos unimos inmediatamente con todo el afecto y el respeto mutuo que se pueda imaginar. También tuvimos momentos de diversión en México, como en estas fotos en las que visitamos una cantera de plata. Hoy en día, su presencia ilumina mis estancias en el País Vasco con francas discusiones científicas y conversaciones sobre el sentido de la vida, a menudo con una buena copa de vino y un extraordinario plato de pescado. Por último, pero no por menos importante, quiero agradecer muy especialmente al apoyo que siempre he recibido de mi familia. Elisabetta, mi compañera, durante todas las etapas de mi carrera científica, sacrificando proyectos propios, intentando comprender la importancia de una dedicación intensa y de tantos viajes que en algunos casos hemos podido compartir, pero que también han supuesto ausencias frecuentes. Mis hijos, Carlo y Emma y aquí Carlo, que tan han sufrido mis ausencias y que desde poco han empezado a vivir sus propias vidas. Y Carlo me ha dado un nieto que se llama Matías, que tienes ahora casi 10 meses. No puede estar más orgulloso de ellos en todos los sentidos. Gracias.
Muchísimas gracias, Mauricio, por esta charla tan estimulante. Si alguien quiere hacer alguna pregunta.
Español.
Como eres un académico extranjero, no sé si preguntarte en inglés o
Lo que quieras. Siéntete libre.
Muchas gracias, Mauricio, por esta excelente presentación, acorde con lo que has hecho siempre. Y sobre todo, muchas gracias por enseñarnos también tu lado humano, que es todavía más grande que el científico que ya es. Entonces, muy contentos y orgullosos de acompañarte en este momento tan importante en que te haces miembro de nuestra academia. Entonces, vaya eso por delante. Quería hacer una pregunta puramente científica, porque no has mencionado los nanotubos de la naturaleza del propio nanotubo. No has mencionado si que se aparezcan en forma de bundles, de madejas, dificulta su uso. He visto que en la primera parte has utilizado nanotubos de doble pared, me imagino para preservar intacto un sistema PI, pero en la segunda parte ya son una versión de pared sencilla, pero tampoco, no sé si valen igualmente semiconductores que conductores en la naturaleza de nanotubos. Sí, en una pincelada general, ¿qué tipo de...?
En general utilizamos nanotubos de carbono a pared múltipla, con capa múltipla, porque son conductores y funcionan mejor en general, y son menos agregados, son más económicos, no cuestan casi nada. Los nanotubos de pared de cingula son extraordinariamente pegados y cuestan mucho y tienen un montón de metales de la síntesis.
¿Cómo compara? Porque el tema del metal yo creo que es muy importante en algunas, bueno, básicamente en las dos, pero ¿cómo compara frente al grafeno, que sé que también has hecho cosas?
El grafeno tiene propiedades diferentes, así que en algunas aplicaciones mejor el grafeno, en otras mejor los nanotubos de carbono. Por ejemplo, hemos utilizado los nanotubos de carbono, el grafeno y los nanotubos de carbono en la reparación de la médula, y hemos visto que tienen un comportamiento completamente diferente. Y los nanotubos de carbono son mejores porque son capaces de, como son tubulares, pueden entrar en las células e interaccionar con mayor efecto.
Una pregunta, el hecho de que sea semiconductor o conductor, ¿eso
implica sí, pero en el caso de multiwall no, son conductores y ya está.
Sí. Hola, bueno, muchísimas gracias por esta conferencia y es un honor para nosotros tener aquí como académico corresponde en extranjero. Realmente es magnífico. Quiero hacer una pregunta técnica, quizás la haga en inglés, una pregunta técnica. It has to do with the first part of your talk. Well, you have described your research in connection with, for example, the mechanism of photosynthesis and the role of the different approaches you have mentioned. But I have a very simple question, which is, do you think that now that we have in our society a great need of hydrogen, say liquid hydrogen is fashionable, as you know, in the midterm, and certainly in the long term, would that procedure of directly splitting water with solar energy, for instance, be competitive with the present approach of using the light to produce electricity by the normal cells and then using that to decompose the water in the normal hydrolysis thing?
Well, in principle, yes, because it is only a technical problem now. The one problem could be the stability of the system with time. So this needs to be checked carefully. And then we are actually already in contact with an industry to place this, to start obtaining results on a larger scale. So it will need some time, of course, but it might be more convenient, yes. We hope so. In the midterm, yes. Well, let's say 5 years.
Okay, Professor, thank you very much also for your very, very interesting presentation. In the first part, I have a question. Did you try to use other, you just were talking about the graphene, but other semiconductor or semiconductive nanostructures like 2D materials, in which the edge states are very important for the properties of to link anything else. Like in your case, you need to link there the Prato reaction is what you need, no? Is possible a Prato reaction in a different kind of material?
We have tried the reaction on graphene and carbon anyway. On others, we never tried.
Anybody else has done that?
I'm not aware of that, no.
Okay, thank you. Thank you. I think it's enough. Thank you.
Bueno, muchas gracias por la presentación. Yo tenía una pregunta sobre el principio de la charla, ya que both of you are involved in the work. I would like to ask it in English. So the photosensitizer is positively charged and the complex is negatively. And you use a sulfate, a percentage. But I suppose that the photosensitizer was attached to the nanotube. That's not right.
No, there are no nanotubes in that.
And you can't attach it to the carbon nanotube, the photosynthesizer.
This is something that we might want to do in the future because when preparing the electrodes, the carbon nanotubes or other carbon structures with like carbon nanohorns, for instance, which are more porous, they might help the transfer of electrons from the catalyst to the electrode. So it might be that we may need that, but in the case I showed and Marcella showed this morning, there were no carbon nanotubes.
No, we're not. Okay. And if I can ask another one, in the second one, how do you apply the carbon nanotube to the spinal cord in the in vivo?
You have to do surgery.
You have to apply it surgery.
Yes, unless we find a way of producing this
A cell or something.
thermal polymers that are liquid at room temperature and then become solid when inserted in the body. This is another possibility that we are exploring. And so in that case, it might be sufficient an injection.
Okay, well, thank you.
Do we have any additional comments or questions? Otherwise, I think we can close the session here. And I don't know if the president of the session.
I thank you, both presenter and talker, and we conclude then our scientific session for today. Thank you very much for assisting and taking part in the discussion. We'll see you next time. He is so often in San Sebastián. Estás tantas veces en San Sebastián que nos visitan en la academia más veces. ¿A que sí?
Claro que sí.
Claro. Muchas gracias. Y un aplauso. La entrega del certificado la vamos a hacer para la foto aquí, pero para el libro de honor arriba,
Vale.
en el despacho del presidente mayor de la academia,
Vale.
que no está. El presidente, está bien.
Hola.